So we will continue today with a lecture on the statistical assumptions, especially related to the hypothesis testing. So normally there are three different assumptions that should hold. We will focus today on the first one, and that one is that we will perform a small number of tests. So let's see. So look at this sentence. So if the fishing expedition catches a boot, the fishermen should throw it back and not claim that they were fishing for boots. So in a way, let's say that we are looking for which are the genes that make a difference between two different conditions. So maybe one is healthy, the other one is some particular disease, and we analyzed 20,000 genes. So just by chance, we know that even if there is no genetic trait that is related to this disease, just by chance, 5% of our genes, so that is 1,000 of them, will be identified as related to it. And this 5% comes from our confidence level, that we normally do our confidence tests, our hypothesis test, we do it with a confidence of 95%. So in a way, this is like fishing boots. So we don't know exactly what we are fishing for, and then we fish something and we claim, oh, this is what I was looking for. But the hypothesis test, this 5% was chosen in an environment where it was supposed just to do 1, 2, 3 hypothesis tests. But now, with our current technology, we are able to do 20,000 hypothesis tests simultaneously, one hypothesis test per gene. So on average, we will get 1,000 positive results that are not really related to our healthy or disease condition. So we should correct for the alpha. So the alpha that typically is 5%, we should lower it. There is one correction that is very easy, that is Bonferroni. So if we will do k comparisons, what we have to do is alpha over k. So that is the alpha we should use. And so if in our example of 20,000 genes, instead of using 5 to the 5 times 10 to the minus 2 as so 0.05 as the threshold for the p-value, we should use this 2.5 times 10 to the minus 6. And the family-wise confidence level of these 20,000 tests now is still 5%. Bonferroni has been shown to be sometimes very conservative. And then there are some other kind of corrections. One of the most famous one is this Benjamini-Hochberg false discovery rate. So a simple way to apply it is you take the threshold of Bonferroni and then you multiply it by 1, by 2, by 3, by 4, by 5, and so on. And then now you take the sorted p-values. So the sorted p-values, let's say that the best p-value that you have observed in your data is 10 to the minus 9, then 10 to the minus 8, 10 to the minus 7, and so on. Now you compare this p-value to the multiplied threshold. So 2.5 10 to the minus 6 times 1 stays the same. This p-value is smaller than that. Then this gene would be flagged as significant. Then you have 10 to the minus 8. You have this value multiplied by 2. And then since the p-value is smaller than the threshold, this is again significant, and you keep on comparing, and at some point, for instance this one, 10 to the minus 4 is not smaller than 1.5 10 to the minus 5. So from this point on, all the genes would be flagged as non-significant. And now you can see that we have a much smaller amount of positives and false positives. And this, so people doing, for instance, gene analysis and microarray analysis are very much aware of this problem because they use really many tests. And in some other context, we are also doing not so many tests as 20,000, but we may increase the number of tests. So, for instance, let's say that we are studying the effect of drug A and drug B on the survival time of patients with some coronary heart disease, and we may make just one hypothesis test between group A and group B, or we may divide the two groups into subgroups depending on the condition of the patient. So, for instance, the number of arteries that are affected, the ventricle state, whether it is normal or abnormal, and the electrocardiogram, whether it looks normal or abnormal. Then we have 8 groups, and in these 8 groups, for each one of the groups, we compare drug A and drug B. I don't mean it doesn't make sense. It makes sense to make this subgroup comparison, but we are starting to do many tests. So instead of just one test as we planned at the beginning, now we are doing 8 tests. That is almost an order of magnitude more. We are still far from the 20,000, but we should worry a bit more about the alpha that we use, the confidence level that we use to compare our p-values. And what is not allowed at all is to start doing these subgroup comparisons once you have seen that the comparison between the two groups. So you initially plan to do a comparison between two groups, A and B. It doesn't work, there is no significant difference. And then you start dividing in subgroups and see whether in one of the subgroups you have a significant difference. And the reason for that is unless you have an extremely low p-value, and we have already seen that the p-value is a very unstable measure, so it can look as really small when really it is coming only by chance. But then you have taken the decision of looking at the subgroups after looking at the result of A and B. And then, since you are increasing the number of tests that you're doing, you might incur in this problem of just by chance one of them is significant. There are other situations in which we are implicitly increasing the number of tests. So let's say that you make an experiment with just 12 individuals, and the p-value looks like it wants to be significant. So let's say it is 0.07, that is close to the 0.05, but it is just on the other side of the limit. So then you decide to add a few more samples, and then you add 4 samples more. So now you have 16, still not significant. Then you add 4 more samples, still not significant. You add 4 more samples, now you have 24, and now it is significant, and then you stop. So the problem of this is that you stop only after once you find a significant result. And since we know that the p-value is an unstable measure, then it might jump from one side to the other of the threshold. And since your procedure has been to stop after the first significance, then you might just by chance have fallen into the significant range. So it might be that if you continue your experiment by adding 4 and 4 and 4, then you are back again to the non-significant region. But you stopped and you didn't continue. So you took the decision of continuing the experiment once you have seen your your results. There are ways to do this sequential addition of more and more samples, but the trick is that they take the significant level into account, and then they use different significances for each one of the comparisons. And this addition of more and more samples, they are planned from the very beginning. They are not, the decision is not taken only after looking at the data. This is called sequential data analysis, and if you are interested, you may look into it. Then this is another situation in which we are increasing the number of tests somehow. So let's say that 5 children in a particular school developed leukemia last year. So is that a coincidence? Or does the clustering of cases suggest the presence of an environmental toxin that caused the disease? And then parents should be very much worried about it. So you may compute the probability that 5 children in a particular school would all get leukemia this year. And this probability is calculated through a binomial distribution in which you need to know what is the overall incidence rate of leukemia in children, and then the number of children enrolled in the school, in that particular school. And the probability, I'm sure, is rather low. So parents are around, this is very unlikely. But that school came to your attention only because there were 5 children that developed leukemia. And somehow you may think of all the schools that are in a country, for instance, let's say UK as a country. So there are really, really many schools, so thousands of schools, and only one of them came to your attention because of these 5 children developing leukemia. But so the question is not what is the probability that in that particular school 5 children develop leukemia. The question is what is the probability that in these thousands of schools there is one in which 5 children can simultaneously develop the leukemia. And now the probability is much, much higher, because it is somehow multiplied by the thousands of schools in UK. So in a way, we are also in this setup in which we are doing many tests at the same time. And let's say that you have an experiment. You have designed this experiment according to some primary outcome. Those are the variables you care the most and where the statistical analysis will be focused. So you try to identify differences between 2 groups in this particular variable. But then, as part of the research, you also measure some other variables. These other variables are secondary outcomes. These secondary outcomes may strengthen the scientific argument of the primary outcomes, and they may lead to new hypotheses to study. So you may identify patterns in the secondary outcomes that are really interesting, and then they should be the primary outcomes of a future study. But if you measure many secondary outcomes, you should expect that some of them are significantly different between different groups just by chance, because of this type 1 error in which there is no difference, no real difference between the 2 groups, but just by chance you declare them to be significant because you were unlucky with your samples. You may change the primary outcomes if for the research worldwide has advanced, and now there is a better understanding of how the disease progresses, and then you know that now you should look at this other outcome as a biomarker of your disease. But you shouldn't take this decision after looking at the data and after looking at the variables with the lowest p-values. So the lowest p-values remain. P-value is rather unstable. It is helpful. I don't mean it is completely crap, but it is unstable. So taking decisions based on the p-values alone is not really a good decision. So after looking at the data, you shouldn't decide the definition of the groups. So comparing drugs A and B in pieces patients, because I have drugs A and B and they don't make difference, and then I start to look what is the subgroup for which they make a difference, and I found that pieces patients, they have a difference between A and B. So this subgroup definition, probably it is just by chance. If you expect many different ways of grouping, some of them will be significant just by chance because of this type 1 error. Then you shouldn't choose the important variables for regression after looking at the data. If you have many variables, you might find that the drug response is really a function of the mother's age and Real Madrid score that week. So you might always find significant correlations, but just by chance. So if you look many different combinations of predictors, some of them will be significant by chance because of the type 1 error. After looking at the data, you shouldn't change the pre-processing of your data. So sometimes it makes sense to make the logarithmic transformation of the data, because really the data follows, for instance, a log normal, and then after taking the logarithm, it follows a normal. But this is something that you know in advance. What you can note is, after looking at the data, you transform your data in many different ways, and these many different ways includes transformations. They include outlier rejection, so trying different ways of rejecting outliers, or smoothing the data. Smoothing is particularly bad because depending on how you smooth, you introduce correlation between the measurements, and then the assumption of independent measurements is broken for the hypothesis test. So if you look at many different pre-processing schemes, just by chance, one of them will make a difference between the groups. Or analyze the data in multiple ways. So trying all the testing possibilities in a program. So one tail, two tails, parametric, non-parametric test, just to see if one of them shows a significant difference. So if you increase the number of tests, and we have seen already a few situations in which you are doing, just by chance, because of the type 1 error probability, you will find significant differences. So you should always be skeptical about results that have been obtained by data torture, so manipulating the data a lot, or p-hacking, so trying many different ways of testing and data transformation until one of them finds a significant p-value. And if you don't do that, if you keep on analyzing the data in many different ways after looking at the data, you might at the end finish with something of this kind. So this today's random medical news. According to a report released today, coffee can cause depression in twins. And this is just because you try so many different things that the type 1 error plays against you. And unless you take measures like the false discovery rate or Bonferroni correction, Bonferroni is too conservative. But otherwise, you can easily find differences that are produced just by chance, but because of being unlucky with your sample. So this is all for today, and see you tomorrow.